Hello everyone and welcome to part 3 of C++ Tetris. Last time we made our board, let's actually center it on the screen. Here I have tried different values and I think these ones look good. It's time we addressed these magic numbers we have in our code. Generally, you don't want to have raw numbers thrown inside of your code like this. First of all, their meaning isn't obvious. If someone wants to know what these numbers mean, they're gonna have to check the constructor for the board and see what it takes. And second of all, we have these numbers scattered all over the place. If we want to change them, we're gonna have to go through different files to find them. I think it would be better if we make a header file where we put all of the settings for our game. We add a new header file, call it settings.h. Here we're gonna make a namespace, I'll call it settings. So, what kind of variables are we gonna need? In main.cpp we have screen width and screen height and the frames per second. So let's copy these, throw them here. Let's actually make them constexpr. Same for the FPS. And marking them as constant expressions pretty much means that they are known at compile time. We know them as of writing this code, and this is gonna allow the compiler to do some nice optimizations. We're also gonna need the cell size and the padding, like this. And we're also gonna need a couple of vectors, one for the position of the board and the second for the width and the height. Here let's include vector2. We go constexpr, vec2 of ints, board position. We give it these values, and for some reason IntelliSense is complaining. Expression must have a constant value, cannot call a non-constexpr function. And what this means is that currently our vec2 doesn't support being created at compile time. Let's analyze our vec2 constructor for a second. If I give you the exact values of x and y, do you need anything else to be able to make a vector? Not really. If you have the x and y values, you can create a vector right now on the spot. So why are we waiting until runtime to create our vector? We can do this at compile time. We can enable that by marking the constructor as constexpr. And now if we check our settings, we can see that the compiler is happy, because we have enabled our vector to become a constant expression. Notice that we did not mark our default constructor as constexpr, and yet we are still able to create a default vector. That's because default constructors are implicitly constexpr. Now we can add our board width and height vector, just like this. Now if we hover the mouse over board position, for example, we're gonna see that IntelliSense does know what the value is going to be. And this is a good sign that the compiler knows about it, because if we go int x equals 5, for example, and we hover over it, the compiler doesn't know what x is going to be. It has to wait until runtime to assign this value to it. But it's not the case with constexpr. Okay, so now we can just go to game.cpp, include settings. Let's move assert up, actually. This is better. And now we can just go settings, board position, and settings, board width and height, cell size, and the padding. We can indent this to make it clearer, and we can do the same for main. Go include settings, we can delete these guys, and here we go settings, screen width, and settings, screen height, and frames per second. Now every time we want to modify the settings, all we have to do is open settings.h and modify our values directly in here. It's pretty nice to be able to make the compiler calculate stuff at compile time. Keep in mind that just because I marked the constructor as constexpr doesn't mean that every single vector is now constexpr. The constructor can choose between creating constexpr vectors or normal vectors, depending on the context. So here I'm calling the constructor with 2 constexpr values, so it's going to be a constexpr call to the constructor. However, here I'm creating a vector using 2 runtime variables, and this is not going to create a constexpr vector. But our vector class still doesn't support constexpression fully. Let me show you an example. Here I have created a vector2 and initialized it with a constexpr call to the constructor. This works fine, the compiler knows about the values. Now what if I want to add 2 vectors together? And now IntelliSense is complaining. Expression must have a constant value, cannot call non-constexpr function, the plus operator. So the same rules are going to apply to our operators. If we want to be able to add two vectors at compile time, we have to make them constexpr, like this. And now the compiler has no issue calculating this at compile time and having the correct values. Now instead of all of this, it's just able to replace it with this. Well, of course, this isn't a great example, we could have done it from the beginning, but imagine if it was a super complicated calculation. Being able to do it at compile time is gonna greatly help us with performance. So we should make every single one of our operators constexpr. Just like this. And what about the getters and setters? Should they be constexpr? Here I create a first constexpr vector, and then I try to create a second one using getX and getY. And we get the exact same error, it's not constexpr. So in short, yes, they should be constexpr. Just like this. And now the compiler is not complaining anymore because getX and getY can be called at compile time. What about the setters? Let's try to call temp1.set, and we can't. Maybe it's because they're not constexpr? Okay, so we make them constexpr. Try again. And we still can't. Well, don't forget that constexpr expressions cannot be modified once they are created. I can't call any setter on temporary1 or temp2. So what's the point of making them constexpr, you might ask? Here I have created a constexpr function, and inside I have created a vector, and then initialized it using setX and setY. Keep in mind that inside of constexpr functions, we can only call constexpr functions. So if we did not make setX and sety constexpr, this would not work. If I remove this, and then try to compile, the compiler is going to tell us that temporary function cannot result in a constant expression because it's trying to call a function that is not constexpr. If we give it back, we can now compile with no issue. So even though setters cannot be directly used on constexpr vectors, they can be useful nonetheless, so we should leave them this way. Again, remember that marking a function as constexpr is not going to force it to be calculated at compile time everywhere. The compiler is still free to choose whether to call the constexpr version or the runtime version accordingly. In this example, it's going to be called at compile time, but in here, it's going to be called at runtime. And now our vector class is 100% compliant with constant expressions. Whoever is going to use it can use compile time calculations to optimize his program. It's great to have a header file where we can put our global variables inside, but there's an issue with this method. It's not obvious, but we are actually duplicating our constants every time we include them. Main.cpp is going to have its own memory for the settings, and game.cpp is also going to have its own memory. Imagine if we had hundreds of constants inside of our settings, and then we included the header in a bunch of files. We would end up making hundreds or thousands of copies of these constants. But why are copies being made every time we include it? And most importantly, can we fix it? To answer these questions, we're gonna have to take a little bit of a deeper dive into how the compilation process goes. We're gonna need to make sure we understand three things: translation unit, internal linkage, and external linkage. The compilation process is divided into three main parts. First, we have the preprocessor, then we have the compiler, and finally, we have the linker. So the preprocessor is gonna take in the CPP and header files. It's going to generate preprocessed files. These files are what we call translation units, and they end with .i. Then the compiler eats the translation units and generates .object files. The linker is gonna eat the object files, slap them together, does some magic, and finally generate a .exe file. So this is an overview of what happens when we compile. Let's take a closer look at the details now. Let's right-click our project, go to Properties, then go inside of C, C++, Preprocessor, All Configurations, and let's enable Preprocess to a file. And this is going to stop the compilation process right after the preprocessor finishes working. Here. Let's confirm, and now let's try to build. And you can see that we get an error. It's from the linker, and it says that it cannot open the board.object file. And that's normal because we said that the object files are generated by the compiler, which did not do its job because we stopped at the preprocessor. Okay, now let's right-click the project, open folder, and go inside of debug. And here we have a bunch of .i files. They are preprocessed C++ source. There is one for each CPP file in our project. Let's open main.i. So we see a whole bunch of random stuff, a lot of emptiness for some reason. Let's scroll all the way down, go a little bit back up, and this is familiar. This is our main function, and right above it, we have our global const expressions, and right above it, we have our game class, and above, our board class. What's going on in here? Let's take our main.cpp and put it to the side, so we can compare. It looks like we have the exact same thing as our main.cpp, except that the comments have been removed. They have been replaced with blank lines instead. And then we have our settings, and that makes sense because we included settings here. So the preprocessor is going to open settings.h, copy everything that's inside, and paste it in here. Then above we have our game class, again because we have included game.h, so it goes inside, copies everything, and pastes it. Above we have board, because inside of game we have included board, and then above it we have a whole bunch of weird stuff that we're not familiar with, and that's normal because it comes from the string library. And the preprocessor keeps doing this for every single include in our code until it finishes everything. Once it's done, we finally have what we call a translation unit. It contains everything the compiler needs to process this file individually. I said individually because even though the preprocessor is going to generate a preprocessed file for every CPP file, every one of these files is going to be processed separately by the compiler. Now let's open up game.i, open game.cpp, and put them side to side. Scroll all the way down. So, it's pretty much the exact same story. Everything has been copied over. We also notice that these assertions have been transformed into this weird code here. And that is because in reality, assertions are preprocessor macros. If we control-click on it, we can see that it's defined using #define, and anything defined by #define is going to be taken care of by the preprocessor. So if the preprocessor finds an assertion, it's going to be replacing it with this stuff. And that's exactly what we see here. So this is fine. If we scroll up a little bit more, we find that we are calling setCell. And this is fine, right? Because we have included game.h, which in turn includes board.h. So we should find board somewhere around here. And yes, here it is. But this is only the declaration of setCell. How does it know what setCell is supposed to do? Does it get it from another place? If we open up board.i, we should find the implementation here, right? Because it's implemented in board.cpp. So if we go down and search for it, here it is. So we can say that game.i is getting the implementation from board.i, right? Well, not really, at least not directly. We said earlier that every translation unit is processed on its own by the compiler, so there's no communication between translation units. It's why in reality the compiler doesn't know what setCell does in this translation unit. Then how does the program still work? Well, that's where the linker comes in. When the compiler doesn't know about the implementation of a function, it's going to leave it blank. Then the linker is going to come in and fill in the blanks with the address of the implementation. Basically, the linker is going to be responsible for sharing stuff between translation units. When a resource is shared across translation units, we say that it has external linkage. The resource is linked to something that is external to the translation unit in which it lives. So this forward declaration is externally linked to this implementation. We also say that the implementation is externally linked because it's shared across other translation units. And this is very useful. This way, we don't have to copy the whole implementation every time we want to use it in another CPP file. Okay, so that's good to know. But how is this relevant to our constants duplication problem? We have included our constants in main.cpp and in game.cpp indirectly because they're included in game.h. Let's put main.i and game.i side by side. So, where's the problem? I don't see anything wrong with this. The preprocessor is copying and pasting the settings file as it should. Well, the issue isn't with the preprocessor, it's with the linker. Constexpr variables by default are internally linked. When a resource is internally linked, it's only available inside of its own translation unit. It's hidden from the linker, so the linker can't share the resource with other translation units. What's happening here is that every translation unit is forced to have its own set of constants, because it doesn't have anywhere else to get them from. They are internally linked, they have to be attached to the translation unit that uses them. So it creates its own memory to store the constants for itself. Wouldn't it be better if we could make them behave the same way the function declaration and definitions do? Have one actual definition in a translation unit, and then share it across all of the others. Well, that's where inline comes in. Marking a variable or a constant inline is a new C++ 17 feature, and it does something very simple. It forces the variable to become externally linked, then it forces the linker to only pick one instance of it. So let's mark every single one of our constants as inline. Now let's recompile. Oh, and also something to note. Apparently when we try to recompile directly, we're gonna get errors like these. When we enable preprocess to a file, we actually have to rebuild the whole thing every time. So we can just go rebuild solution. This time it works. If we check the preprocessed files again, our constants are now marked inline. The compiler still redefines them in every translation unit, but the linker is gonna see them and go, ah, these constants have external linkage. I can actually keep one of these two definitions, and then link the other one to the definition I chose. The linker is free to choose whichever definition to keep. They are all identical. Now, no matter how many times we include our settings, they're always gonna take the same amount of memory. Just enough to hold all of them. Once you understand what's going on under the hood, you realize that all inline does is mark the variables as externally linked, and informs the linker that it should only keep one instance. Inline isn't some magical keyword that's gonna automatically optimize your code. Nothing is, and that's why it's important to understand the tools you use. This website is called learncpp.com, and this post is made by Alex. It's a very good read about the exact issue we just tackled. With the knowledge you have now, it should be an easy read. And even if you didn't get everything I said, read it and it should clear things up. LearnCpp is actually a pretty good resource. They have many posts about different C++ things. They even have dedicated posts for external and internal linkage. Okay, that was a lot of theory, and I hope you learned something from it. I could have just added inline and called it a day, but I prefer when we understand what's going on. It may have been a pretty long detour for an optimization, but having a deeper knowledge is important, so I think it's worth it. Alright, let's make our project compile normally once again. We go to Properties, Preprocessor, and here we go No. We've had enough of your preprocessed stuff. And if we compile, everything works just fine. And our code is as fancy as ever. Let's add a border to the board so that it looks decent. We're gonna need some kind of rectangle borders. Luckily, Raylib provides a function to do just that. It's called drawRectangleLines EX. It uses a rectangle and a line thickness and a color. Unfortunately, the rectangle is just as dumb as the vector. We could make our own rectangle class, but we can actually easily represent a rectangle using a couple of vectors. No need to bother making another class. So let's wrap this rectangle class function. Instead of taking a rectangle, we're gonna take a vec2 of ints for the position, and a vec2 of ints for the width and height. Here we go draw rectangle lines EX. So we're gonna need to construct a rectangle. So the top left is gonna be position.getX, position.getY, and the width is just gonna be width height.getX, width height.getY, and now we give it the line thickness and the color. And the compiler doesn't like this because cannot be called with the given argument list. Okay, so this error isn't very helpful because the Raylib function is being shadowed by ours. But I know what the issue is. The rectangle struct is actually a bunch of floats, and we're trying to initialize it with a bunch of ints. What we need to do is cast them to floats. Just like this, and now the compiler is happy. Remember, when we have a dumb structure like this, we can just initialize it with angle braces and give a value for each one of these in order, just like we did here. We can add the exact same assertion as draw rectangle to prevent drawing outside of the screen. Let's also make sure that the line thickness is above 0. In board.h, we can add a function, draw border, make it const. We call draw rectangle lines. The position is going to be screen position minus half of the cell size. The width and height is going to be width times cell size and height times cell size. Remember, we need to count the number of pixels from the top to the bottom and from the left to the right. So this is going to give us the exact width of the board in pixels. And we should probably add to it half a cell size. Okay, when we use a plus, the compiler is not able to deduce that this is supposed to be a vector. So we're going to explicitly tell it that it's a vector. The line thickness should be cell size divided by 2. And the color, we actually should give it a color, but we'll make it white. And this looks about right. So let's try to call it inside of draw. So you go draw border and hope that this works. Please work. And it looks like, actually, it looks like we have eaten a little bit of space here. And I think it's because of this. We're supposed to add a whole cell size, not half one. And there we go, this works better. Okay, to make sure the video doesn't get too long, we're gonna stop here for now. Next episode, we're gonna tackle the most important thing in Tetris, the tetrominos. So thank you for watching, and let me know if you like this type of theory. It's not something you learn everywhere, but I think it's important. Anyway, until next time, take care of yourself, and see you soon.